Hi viewers, welcome to my class on mechanics of materials. In this class, I'll introduce the basic concept of stress. When a material is subjected to loading, internally the material will resist the external load applied. Stress is internal resisting force per unit area exerted by a material when it is subjected to external forces. Internal resistance offered by the material against external loading per unit area can be considered as stress. Consider a bar subjected to an axial pull P. Let us consider the right portion of the bar. The external load is P. To maintain equilibrium, there should be an opposing force, and this opposing force is known as resistance offered by the bar. So it's the internal resistance offered by the bar, and this internal resistance is distributed across the cross section. It is not a point load, it is distributed over the entire cross section. And when equilibrium exists, this external load and resistance, they are equal. So I have written that internal resistance is equal to P. So in total internal resisting force will be equal to the external load. Now this internal resistance per unit area, that is unit area, if you consider this, a large amount of area is there. Unit area, if you take, what is the resistance offered by that material in that unit area, that is known as stress. So stress is internal resistance offered per unit area of cross section. Suppose the load is 1000 Newton and the area is 100 mm square. 1000 Newton is resisted by an area of cross section 100 mm square. Okay, what is the load resisted by 1 mm square? This 1000 Newton is resisted by 100 mm square of cross section. When external load is 1000 Newton, even internal resistance has to be 1000 Newton. So internal resistance is 1000 Newton. 1000 Newton is resistance. 1000 Newton resistance is offered by this 100 mm square cross section. What is the resistance offered by 1 mm square cross section? That is stress. So 1000 for 100 mm square cross section. So 1 mm square cross section, it is 1000 by 100 or 10 Newton per mm square cross section. 100 mm square cross section is offering a resistance of 1000 Newton. The question is, what is the resistance offered by 1 mm square cross section? So it is 1000 by 100 or 10 Newton per mm square. So that is the amount of resistance offered by the material per unit area when it is subjected to external loading. So stress is internal resistance offered by a material per unit area when it is subjected to external loading. And this, in this figure, I have shown tensile forces, and corresponding stress is tensile stress. And when you call it as a normal stress, when this force and resisting area, they are mutually perpendicular, or this area, resisting area, is vertical plane and the force is horizontal. So the force is perpendicular to the resisting area, then you can call it as normal stress. So normal stress can be either tensile or compressive. In this case, it is normal stress. Why it is normal stress? The force is perpendicular to the resisting area, or resistance is perpendicular to the resisting area. Resisting force is perpendicular to the area resisting that load. So it is normal stress. Because it's trying to elongate the body, it is tensile stress. So it is normal tensile stress, or you can say tensile stress. We usually omit this normal. It is understood that is a tensile stress is a normal stress. Similarly, you have compressive stress also, normal compressive stress if a load is compressive. So if the load on the material is normal to the resisting area, the stress is known as normal stress. Tensile stress and compressive stress are examples of normal stress. And stress you can calculate as force divided by resisting area. So this is tensile stress, and tensile stress like external load, this internal resistance, again in internal resistance is distributed, and per unit area what is the amount of resistance offered, that will give the stress induced in the material. And area you can calculate for a circular cross section, you can calculate area as pi by 4 d square. Okay, load divided by load, resistance will be equal to the external load. So resistance divided by area, that is resistance is P, that is load, divided by area is pi by 4 d square, that will give the stress. In the previous example, here the area is calculated because it's a rectangular cross section. You can calculate the areas as B into H. Okay, resisting area is BH and load is P, and resistance also will be equal to P. So stress induced will be P divided by BH. So in this case it is P divided by pi by 4 d square, because resisting area in the form of circular cross section. So it's a normal compressive stress, compressive, because I have shown the compressive force, and here it is resistance is opposing that external force, and the bar portion of the bar is under compression. So the entire bar is under compression. I shown a section here, and it is compressive stress, and resisting area you can calculate as BH, and compressive stress is P divided by PH. Now this is also a member subjected to compressive stress. You are applying a compressive load, and if you take a horizontal section, it is subjected to compressive stress. We will see the unit of stress. The unit of stress is Newton per mm square, because it's a force by area, resistance force divided by area. Force unit is Newton, unit is Newton, and area unit is mm square. We can use a centimeter square or meter square, but mm square is more appropriate, because usually the area of cross section cannot be in meter square. It is usually you'll get mm square. The cross section will be like all structural members will have a limited area of cross section, so you can take it in mm square, and the forces you can always put it in Newton. Even if it's given in kilonewton, you can take it in Newton. So generally the unit used is Newton per mm square, and it's also equivalent to megapascal. So let us show that how you can convert 1 megapascal and show that it is equal to Newton per mm square. 1 megapascal is, mega is 10 raised to 6 and Pascal is Newton per meter square. So 10 raised to 6 Newton meter, every meter is 10 raised to 3 mm. So 10 raised to 3 mm meter is 10 raised to 3 mm and square of that. So you get 10 raised to 3 square is 10 raised to 6 mm square. So in numerator you have 10 raised to 6 and denominator also 10 raised to 6, that cancels. You get 1 Newton per mm square. So 1 megapascal is 1 Newton per mm square. So if you are expressing in gigapascal, gigapascal is not generally used for stress, but later we study Young's modulus, which is generally expressed, which has got the same unit of stress and is expressed in gigapascal. So you should know gigapascal. So giga is 10 raised to 9 and Pascal is Newton per meter square. So once again, meter square you can write, meter is 10 raised to 3 mm, 10 raised to 3 mm square. So you get 10 raised to 6. Yeah, so finally you get 10 raised to 3 Newton per mm square. Or gigapascal is, giga and mega is, difference is 10 raised to 3, because mega is 10 raised to 6, giga is 10 raised to 9, the difference is 10 raised to 3, giga is 10 raised to 3 times megapascal. So it has to be, since megapascal is 1 Newton per mm square, gigapascal has to be 10 raised to 3 Newton per mm square. Now, similarly, you can also express 1 kilopascal. Kilopascal, kilo is 10 raised to 3. So finally, you get 10 raised to 3 by 10 raised to 6. You get 10 raised to minus 3 Newton per mm square. So kilopascal is a small unit compared to a megapascal, and gigapascal is 10 raised to 3 Newton per mm square, and kilopascal is 10 raised to minus 3 Newton per mm square, whereas megapascal is Newton per mm square itself. So alternately you can use interchange and use Newton per mm square, and megapascal can be interchanged and used. So with this we'll conclude today's class. Thank you for watching.